Okay. There's some homework here, Diana. Here, we can see.
You sent us an email saying 223, 224. Here's the yeah. You guys need to split up.
Grace, I have your homework here. Brian, I have your homework here. Tatum, I have your homework here. Lexi, Rosa, and Ali. Sage.
Are you going to? Yes. We were here, there was like 5 tournaments. We have to wear like the water throughout the day. Yeah.
Okay, I have your homeworks here. I think I'm done grading all of them. If you have any questions about your homework grade, you can just send me an email and we can set up a time to talk about those. If you gave me a hard copy of your homework, I'm gonna put them in the bin outside my office so people can go and pick them up. There's a homework due on Friday, this Friday. I'm gonna try to take copies of the problems and put them with the homework, just in case you have the different editions, so you know exactly what problems we need to be solving. I think that's it. Questions about the homework so far? No? Okay, so a couple of things. So when I was grading your homework, I saw that people were making a very specific mistake with the conversions. We didn't cover conversions during class because you guys have done those before. Like you see it in chemistry, you see it in biology, you see it in all your IPHS. So I didn't want to spend much time on those. I think I pretty much am very familiar with how to do it. I know it's a particular kind of problem. For example, if you want to convert 100 centimeter square to meter square. So many people, what they did is like, well, I know that 100 centimeters is 1 meter, so therefore 100 centimeters square is going to be equals to 1 meter square, and that's wrong. Okay? So if you have 100 centimeters square and you want to convert that to meters, well, you know that 1 meter is 100 centimeters, and that's fine. But because you have square, you have to do this conversion twice. So this go to square. So 100 centimeters squared is actually 0.01 meters square. If I were to have 100 centimeter cube, same thing, I will have 100 centimeter. That's my conversion, but because now I have cube, this has to be cube too. Okay, so this will be 0.0001 cubic meter. Same thing happened with pounds per cubic feet. So if you have 10 pounds per cubic feet, well, you have 2.2 kilograms is 1 pound. There's no exponential on the pound, so that one stays like that. But feet have the cube. So I know that 1 feet is 0.303, something like that, meters. But because we have cube, these have to be cube. And I think on your homework, I don't remember, I think you got like a 560 kilograms per cubic meter. So be careful. Most of you got correct, but I think there was some of you that got this wrong. So if you have this exponential on the units, that has to be reflected also when you do the conversion. Otherwise, you're missing dimensions. Okay, makes sense? Okay, that's one thing. The other thing that I want to talk before we go to the topic is that so far, all the problems that we've been talking about haven't been basically just very simple problems involving boxes and elephants and stuff like that. And we haven't talked at all anything about the human body. So I probably should have introduced problems with structures a little bit earlier. I probably made a mistake. But one of the things that I wanted to do in these first 3 weeks was to make sure that everybody had the same background. I have the same baseline in terms of concepts and to understand how to work with trigonometry and how to work with frame of reference and do the free body diagrams. That's basically the main objective that I wanted, because that translates to everything that we're going to be doing in the future. So if we work with very complex structures, then if you look, for example, the structure of your hip and you're trying to find out the forces on your hip, there's a lot of angles and forces that may be a little bit distracted. So I rather focus right now in a simple box that I know that they're going to be very simple connections, and then we can go and work with a more complex structure. So next class, starting on Friday, we're going to start with chapter 7 and 8. That is basically, we're going to start working with the human body. We're going to be focusing right now with the skeletal system. And we're going to be applying the things that we've been seeing so far, we're going to be applying to the human body. So hopefully it will make a little more sense. I'm not going to say that it's going to be super exciting. Like if you think so far it's been boring, the next thing is going to still equally boring. It's just going to be boring with something that you know more, but it's the same. Sorry. Physics is fun, but not for everybody. Sorry. So instead of having a pre-quiz or a quiz before the lecture, there's going to be a quiz that's going to be midway chapter 8. So even though we're going to start chapter 7 and 8 Friday, the quiz is due on Wednesday 18, I think, and it should be already on Canvas. We're going to try. The exam is going to be on September 25th. That's a Friday, right? The first midterm, I think, is the 25th. The 25th. I'm not sure. I'm pretty sure it is. So it's going to be on a Friday. It's going to be on your room, so it's going to be online. And we're going to try to cover as much as chapter 8 as we can. But I don't want to move the exam. So I'd rather make the exam cover less material than push the exam forward to cover what I was foreseeing for the material, right? Chapter 7 and 8, I think they're complicated. Like if you haven't problems figure out the free body diagrams for these examples that we have seen so far, chapter 7 and 8, they're a little more complicated. But we're gonna go as slow and repeat as much as you guys need, as everybody needs, so everybody's comfortable. I'll open to have office hours, so everybody's feeling okay. Chapter 7 and 8 are specifically important for all of you that are gonna go in to do any kind of or they want to do any kind of rehab, physical therapy, rehabilitation, sports medicine. They're particularly important. So I know that people want to spend more time on those. Okay, make sense? Okay, any questions? Okay, so the exam, obviously, you're gonna do it on your dorm. You can use your computer, obviously, and you have your notes, you have your textbook. Technically, you're not supposed to be using the internet, but honestly, I don't have any way to enforce that. So The way the exam works is that there are going to be 5 questions, and for each question, there's going to be a pool of 5 different options of sub questions, if you want to say it. So at the end, there's like I don't know, like 100 different combinations that you can have, 100 different kind of exams. So you're probably going to have 2 opportunities to do the exam, and I will keep the highest grade. But if you do exam and then you redo it, you're probably going to get different questions. So it's going to be kind of a toss if you get the questions that you are prepared versus the questions that you're not so sure. And I will give you probably 2-3 hours to do the exam. Okay. Questions so far? Nope. Okay. So the last topic that we were talking about was friction. And today I want to finish friction. So I want to do a couple more problems involving friction. We're going to be talking with a new equation for acceleration, something that we haven't talked so far. So just if it's getting too fast, too confusing, just stop and just ask me. And the people on the chat, again, if you don't understand something and you want me to go slowly, I'm gonna try to check the chat, but if not, just open your mic and just let me know, okay? So I'm gonna go back to this thing. Let me say something. Okay, can you guys see on the chat, can you see the piece of paper? I'm trying something different. So I need someone to tell me if you can see everything. Okay, perfect. Thank you, Karen. Okay, so I think there's actually less delay. No, it's the same. Never mind, didn't work. Okay, so gonna be a different kind of problem. Imagine that we have a turtle, and here's the turtle. And you have a hockey stick. And you're gonna grab the hockey stick and then you're gonna hit the turtle like if it were a puck. And it's just gonna go and just fly. Is any one of you with Dr. Rowe? Good. Oh, don't tell him. So you're just gonna go and hit that turtle like if it were a puck. And we're gonna assume that the turtle has a mass of 2 kilograms. And right now in this part where it's completely flat, I'm gonna assume that there's no friction. Okay, so the coefficient is, all of you, there's a lot of people that work with Dr. Rowe. Don't tell him. You can assume that you have a coefficient mu k of 0. So that means that there's no friction. This turtle is gonna move forward and then it's gonna reach a ramp. Okay, and this ramp is gonna have 35 degrees. And this ramp is going to be made out of, it's going to be grass. So there actually is going to be some friction. So I'm going to assume that this mu k now is going to be 0.5. It's going to have a value of 0.5. Here, at the beginning of the ramp, the turtle is going to have a velocity of 10 meters per second. And it's going to start climbing, it's going to start going up, and eventually it's going to stop, it's going to come to a stop. So the final velocity is going to be 0. Okay, and what I want to find out is what is the distance that the turtle travels on the ramp before it comes to a full stop. So I want to find out what is this distance. Okay, now the way we've been talking about accelerations and velocities and all that stuff, we won't be able to solve this problem the way it's stated, okay? So we're gonna do it by parts, and then at the end, we're gonna calculate what is that distance, okay? So right now, in this flat area, there's no friction. You hit the turtle is gonna have some velocity. There's nothing interesting going on. So we're gonna ignore this part. All the interesting part happens in the ramp. So we're gonna look at the turtle on the ramp. So we need a free body diagram on the ramp. Okay, so start with the free body diagram of the forces on the ramp, then look at Newton's second law equations. Then there's a bunch of math here in between. And then at the end, what I want to find out is what is the acceleration in the x direction. Okay? So what I'm gonna do is I'm gonna set the problem like this. I'm gonna try to let you guys do it on your own. And then if you get stuck, I'll come and help you, and then we solve it together on the blackboard. Sounds good? Yeah, in this case, it's better if you rotate your frame of reference and you have the x-axis parallel to the ramp. No, I have a max extender. My ears are free. So I have a couple of max extenders. So the elastic band is not contact with your ears all the time. And I can make more. So if anyone wants, just let me know and I can make one for you guys. But I have a couple extra right now. So if anyone wants, I make it with a 3D printer. Nope. Yeah, so in this case, rotate the axis, make it parallel to the x-axis, to the ramp. Now, what would be your apply force? Yeah, but you hit that thing, or you hit the turtle back there, and it is just sliding on the ice.
So there's no force here.
Exactly. There's no force. There's no applied force. Like you hit the turtle with a hockey stick, but way behind. But the moment that you hit the ramp, there's nothing pushing the turtle. It's just the inertia that it had.
Oh, no.
So this is square. So they show you axis.
It's trying that. But it's just not like this.
Yeah, I just haven't.
They can have two.
No, we don't have that.
I think that's already in it. Okay, so I don't think this is what. But is there another, because you're gonna have the. I guess I'm trying to think if there's another force that's going to.
You missing the normal force.
Because it just goes parallel to the additional space.
Now, the turtle's moving up, right?
Right.
So which way is going to be the friction?
Is it going to be going towards one side this way?
No, so remember, friction is always going to be opposing the motion.
Oh. Okay.
Always. If the turtle were sliding down, sure, then you will be correct. It's going up.
So since he's going this way, this direction,
And check this. Check the direction of your weight.
forces.
So I will suggest that you draw your turtle here, look at the force to this direction, and then you draw your axis and see where it goes. That's all. The friction, no, but yeah, so I'll do it. Okay, so I'm gonna draw, right now, we only care about the turtle on the ramp. So I'm gonna draw the ramp. I have the turtle over here. It's hiding because it's afraid. And I'm gonna have the weight pulling down, and it's always gonna go down. So the weight is gonna go down. Friction, if the turtle is moving up, then or along the ramp, then friction has to go in the opposite direction. So friction is gonna go in this direction. This is gonna be the weight. And the normal force is gonna be perpendicular to the ramp. So it's gonna go like this. Okay, so those are the three forces. There's no applied force. There's nothing pushing the turtle upward. It's just the inertia that it had at the beginning that is keep going the turtle up. So now on this point, I'm gonna draw the reference axis. So I'm gonna make my x-axis parallel to the ramp. So it's gonna go like this. And my y-axis is gonna be perpendicular to that, to the x. So it's gonna go like this. Okay. So notice how the weight is on the third quadrant. I think this is where most people got it wrong. They put it on the fourth quadrant because some of the examples, when you're going down the ramp, it ended being on the fourth quadrant. So just be careful with that. So your ramp, your free body diagram at the end is gonna look weight is gonna be like this. This is gonna be a 35-degree angle. Friction and normal force. Yes.
How did you know the 35-degree angle is there?
It's a little bit uh, of geometry, but usually this angle along the x-axis is going to be the same angle that you have with your ramp. Okay, so now that you have it like this, what you need to do is write Newton's second law. So you know that Newton's second law is the sum of forces equals mass times acceleration. But because we have, because these are vectors, we're gonna need to decompose it in x and y components. So how does that equation, how does Newton's second law looks on the x-axis and how does it look for the y-axis? Like if it's a static problem, is it a dynamic problem, it's an equilibrium problem, how does that equation looks like? So try to find that one. So in y, did you have an acceleration in y?
I don't know, because it's moving like this way, so.
But now you change your x-axis, right?
So it's not moving?
It's not moving y. So it has to be equal to 0. Yep. Now, now, your weight has y components and x components. Okay?
Yep.
So here, be careful because the weight has some y components and x components. So it's not going to be just like that.
Okay.
Or the normal, yeah.
Okay.
For the that's for x.
So remember, the way we calculate friction is the coefficient. So there is here. And just be careful when you calculate. To explain, but basically is that when you switch your frame of reference and the charge is moving along the x-axis, it's just moving along the x-axis, not moving in the y-direction. So if you look at the displacement in y, it's always going to be the same. So if there's no change in displacement, there's no velocity, there's no velocity, there's no acceleration. Because we're changing the frame of our reference. Yeah. If you will leave it flat, then yes, you will have changes in X to Y, and then the flat becomes the X and Y. So that's what the advantage of rotation function. Oh, two, yeah. Yeah, correct.
I don't see it.
It's a speed against X of the normal force. These will be equals to mass acceleration.
Okay.
Okay, so I'm gonna write down the Newton's equation. So for the x direction, so if you look at your the diagram, the turtle's only moving in the x direction. So on the x direction, we know that go from 10 meters per second to 0 meters per second. So there's going to be an acceleration. So the sum of forces in x has to be equals to mass times an acceleration in x. We don't know what is that acceleration. That's what we want to find out. Now, in the y direction, because we changed our frame of reference, because we rotated that axis, there's no displacement in y. It's not moving in y, just moving along the x-axis. So if there's no displacement in y, there's no velocity, there's no change in velocity, there's no acceleration. So these will be equals to 0. And these are just your two Newton's law equations, your second Newton's law. So what we need to do is to solve these equations. So I'm going to start with the y direction. Okay, and in the y direction, Emma, how you doing? Are you sure?
No.
At all? Okay, can you tell me what forces do we have in y? The normal force and the weight, where we have the y component of the weight. It's not just the weight, it's the y component of the weight, because now the weight is on the third quadrant. The weight is going to have an x component, and a y component. And that's going to be equal to 0. Alexis? Can you tell me what is the y component of the weight?
Well, I don't. Oh, the value.
Not the value, just the
Negative 19.6 35.
mg cosine of 35. Yeah? So you have mg cosine of 35. And Rihanna, do you have the value of the normal force?
Negative 16.06.
16.
16.06.
Yeah, 06. Yes. Okay, so that's the value of my normal force. Now I'm gonna go and look at the at the x direction. Now the x direction. Oh, way in the back. I forget your name. Sorry, Emma. What forces do I have in the x direction?
And the x value of the weight.
Friction and the x value of the weight is going to be, bless you, mx. And can you tell me can you expand this? How do I calculate the friction and how do I calculate the x component of the weight?
So you'll do the 0.5.
Mu. Now this is going to be negative. What else? How can I calculate the x component of the weight? Yep. So this will be negative, again, because pointing in the negative x direction, mg, which is the 1905 that Emma was saying, sine of 35. And this will be equals to ax. Remember, what I want to calculate is ax, is I want to calculate this acceleration. So from here, I can just solve, and I'm going to have minus mu k Fn minus mg sine of 35 over m. And there's other ways that you can try to simplify this equation, the math here, but this is just one way. I'm going to substitute values. So the acceleration is going to be negative 0.5 times the normal force, the one that I calculated is the 1606, minus 2 times 9.8 sine of 35 over 2. And behind Alex, I'm sorry, your name again?
Kaylee,
Kaylee.
I got negative 0.983 meters per second.
So the 0.
Negative 0.983 meters per second.
No, I don't think so. Anyone got something different? Emma?
What is that?
Negative 3.2? Yeah. Let me double check. Either you guys are correct and the people in the morning are really wrong, or so I have 0.5.
Oh, I didn't divide those next. So-
Yeah, I get negative 9.6 meters per second square.
I got that.
Did you get that?
Yes.
Why you didn't say anything?
I don't know.
Oh, by the way, like last week, I make like a terrible mistake on my numbers, and the only person that knows was Mary, but she didn't tell me anything, so the mistake just stay there. And I'm gonna put a note in the YouTube video saying, "Thank you, Mary, for letting me know at the end of the class that I made a mistake." Did anyone got this negative 9.6? Yes. Kaylee, you got it?
Yeah, I multiplied by weight instead of mass.
Okay.
I divided by weight instead of mass.
Okay. You got it? I forgot your name. Lexi?
Yeah, I got it.
You got it? Okay. Next to Alexis, your name is? Eleanor. Okay, you got it? Okay. And on the chat, everybody got the negative 9.6? Hallie, you got it? Okay. I don't know if people are even listening on the chat. I think they're sleeping. They just put it there like, ah. Okay, so what I want to go through a little bit before we go to the next problem is this negative acceleration. Now, a very common misconception, yes?
I thought the problem was to find the distance.
Yes, but before I move forward, I want to make a note on the acceleration. So we got an acceleration in x of negative 9.6 meters per second square. It's a very common misconception to think that because acceleration is negative, that means that the object is slowing down. And that's not true. Just by looking at the value of acceleration, you cannot tell if something is speeding up or slowing down. You need to see what is the direction of the motion and then compare that to the direction of the acceleration. And then you can find out if it's speeding up or slowing down. For example, if you have an object that you drop in from a particular height, the acceleration in this case, like if we assume a frame of reference like this, the acceleration in this case is pointing down. So you're going to have a negative acceleration. But the displacement is also negative. It's also going down. It's moving downwards. So in this case, the velocity increases. So as the object falls down, the velocity is going to go faster and faster and faster until it hits the ground. In the case of the turtle, you have the turtle, and the turtle is moving up, and your acceleration is on the opposite direction. So in this case, the turtle is going to slow it down. So basically, if the displacement and the acceleration have the same direction, then the velocity is going to increase. But if the displacement and the acceleration have opposite directions, then the velocity is going to go down. Okay, so again, you cannot tell just by the value of acceleration if something is speeding up or slowing down. You need to compare that to the displacement, to which direction the object is moving. Okay. Now we're gonna make sense this. Okay, so now we have this value of acceleration, again, negative 9.6. And now the equation, the only equation that we have seen so far that relates acceleration and velocity is this one. We know that acceleration is a change in velocity with respect of time. So we know, and this problem, we know that the initial velocity is 10 meters per second. And the final velocity, because we want to find out when it comes to a full stop, this is going to be 0 meters per second. We have the acceleration, we have the change in velocity, and here we have time. But we don't want to know how long it takes this turtle to come to full stop. We want to find out how far it traveled on the ramp before it comes to full stop. So we cannot use this equation. So we need a new equation that we haven't taught so far. And this one relates velocities, accelerations, and displacement. So this is going to be bf squared equals bi squared plus 2a delta x. Okay, so here we don't have time. We're not involved in time right now at all. We have displacement, we have acceleration. The acceleration has to be in the same direction as the displacement. So this one is acceleration in x. And we have the change in velocity. You've fallen asleep.
No.
I saw the big yawn. There's almost a tear. What was I? Oh yeah, displacement. So from there, what I want to do is to solve for the displacement. So yes, math. So I'm gonna subtract the initial velocity on both sides of the equation. And then I'm gonna solve for delta x. And delta x is gonna be df squared minus bi squared over 2a. Final velocity is gonna be 0. My initial velocity is gonna be 10. And 2 times a is gonna be 2 times negative 9.6. And I think delta x gives you like 5 meters or something like that. Okay, makes sense? Okay, so this is the last problem for today. Oh, sorry. Yeah. This is the last problem for today. When you're done, you can just show me your result, and if it's correct, then you can grab your stuff and leave. This is a problem for page. This is problem 5.29 from your book. So you have a car. The car has a mass of 1,000 kilograms, and it's traveling at a velocity of 40 meters per second. At one particular point, you slam the brakes, and at the moment that you slam the brakes, you are slowing down, and you're going to have a friction coefficient of 0.6. So what I want to find out is how long are the skid marks. And part B will be how much time it takes you to come to a full stop. Yeah. Okay. Yes. 0.6.
Yes. I think everybody got the body diagnosis right.
At the same one.
The same. Yeah, I think everybody got the track, the body diagram.
Yep, so the pre-build diagram is gonna look something like that.
Very good. You can do that, but you can also need to find a way to get.
Hello?
So in the acceleration, so this is correct. The acceleration, friction force, just in the then it has to mass acceleration. So B, this will be equal to mass acceleration.
Is the normal force calculated in that? Yeah, I'm using the normal force, times. Cos friction. Right.
So in X, there's no weight. So. So this one. Yeah, this one. Distance. Is it a seven?
That's great.
Okay, that's good. Okay, sorry. The good news. So during simulation, just be careful. So this will be. So your final velocity, because you want to find out when it comes to a full stop, that the final velocity is not zero. So this will be 0, 40, and you can solve the final velocity. This is your time, this is your distance. So here. So that's there's no weight. So the other examples, because the weight was what had. So,
Yeah. What'd you get?
So,
I got negative. Here. Because you're. Like, look better than that. The. Okay. Why is that negative? I think it's.
Okay. So-
I think it's, that's just, it just goes in.
you do 40 square,
But then it's 60.
but you still have this 100%.
But then I'm still. Then you just have to plug it in.
But that's not right.
Oh. Okay, so I'm gonna say what word negative value should be going, is my answer, but I have a negative time positive displacement, and that doesn't seem right.
Yeah.
I'm gonna do it really quick. Okay, so this will be the two equations that you need to solve. So you have the forces in X equals mass times acceleration, and you have the forces in Y is gonna be equals to 0. So if you look at the forces in Y, you have normal force plus weight is gonna be equals to 0. Normal force minus mass times gravity is gonna be equals to 0. Normal force is gonna be equals to mass times gravity, and then you're gonna end up with a normal force of 9,800. And I think everybody got this one. Now, in the X direction, you only have one force. You only have friction. So friction is gonna be equals to mass times acceleration, and friction is gonna be mu k mass times gravity equals mass times acceleration. The masses can cancel, and the acceleration is going to be negative mu k times gravity, and the acceleration is going to be negative 5.88. There are different ways that you could get that value, but if you got the 5.88, you did it correctly. And that's, if you got to that point, if you got this negative 5.88, you did great. The other part is new, so we need to get used to it. Now, to calculate the displacement, so we're gonna use this equation, Mary. I think this is the one that you have. Bf squared equals bi squared plus 2a delta x. Delta x will be bf squared minus bi squared. And then here you have 0 minus 40 squared over 2 over negative 5.88. Now, Mary, this is the part that is kind of
forgot about a negative sign in acceleration, so that's why I'm doing it.
Okay, so you have this negative and the same with the time. At the time, and to calculate the time, you have acceleration equals delta v over time. Time will be delta v over acceleration, and that will be 0 minus 40 over negative 5.88, and you get a time of 6.8 seconds. Yeah? Makes sense? Yep. Okay. If you have no more questions, then we'll stop here, and I'll see you guys on. I'll see you all on Friday. Is any other question for people on the chat? Everything makes sense?
Thank you.
Tatum, so there are different ways that you can calculate the negative 5.88. You can do it also, you know, look, you know, the friction is going to be mass times acceleration because it's the only force that we have. The friction is going to be mu times the normal force equals ma delta x. And from here, you can solve for the acceleration. Acceleration will be minus mu Fn over m. And this will be negative 0.6 times your normal force that you got 9,800 divided by the mass, which is 1,000. And this will give you negative 5.88 meters per second squared. Oh, crap. I'm so sorry, I forgot. Okay. So there you go. Does it make sense? You have friction force equals mass times acceleration. Then you have, this will be negative mu k times normal force equals m(a)x. And then ax will be mu Fn over m. And then solving it, you get negative 5.88. Okay. Any other question over there? No problem. Okay, so if there's no more questions, then remember, I'm gonna leave the homeworks. If you gave me a hard copy, then I'm gonna leave the hard copy in the bin outside my office. And otherwise, I'll see you all on Friday, those of you that are on Friday, and otherwise, I'll see you when I'll see you guys.